Linear regression is used to predict a quantitative response y from the predictor variable x. Linear regression is made with an assumption that there's a linear relationship between x and y. When there's a single input variable x, the method is referred to as a simple linear regression. When there are multiple input variables, literature from statistics often refers to the method as a multiple linear regression. The core idea is to obtain a line that best fits the data. The best fit line is the one for which total prediction error for all the data points is as small as possible. Error is the distance between the point to the regression line. For simple regression, B0 is the intercept because it determines where the line intercepts the y-axis. In machine learning, we can call this the bias because it is added to the offset all predictions that we make. B1 is the slope because it defines the slope of the line. In both cases, B0 to Bn are called the coefficients, and these values are learned during the model fitting/training step. Training a linear regression model is trying to find out coefficients for the linear function that best describe the input variables. Building a linear model is trying to minimize the error an algorithm does making predictions, and we got that by choosing a function to help us measure the error, also called cost function. There's a lot of literature on how your data must be structured to make best use of the model. As such, there is a lot of sophistication when talking about these requirements and expectations. In practice, you can use these rules more as rules of thumb when using ordinary least square regression, the most common implementation of linear regression. Try different preparations of your data using these heuristics and see what works best for your problem. To start off, let's go with linear assumption. Linear regression assumes that the relationship between your input and output is linear. It does not support anything else. This may be obvious, but it is good to remember when you have a lot of attributes, you may need to transform the data to make the relationship linear. Example of this is log transform for an exponential relationship. The next item is remove noise. Linear regression assumes that your input and output variables are not noisy. Consider using data cleaning operations that let you better expose and clarify the signal of your data. This is most important for the output variable, and you want to remove outliers in the output variable y if possible. Next, remove collinearity. Linear regression will overfit your data when you have highly correlated input variables. Consider calculating pairwise correlations for your input data and removing the most correlated. Finally, Gaussian distribution. Linear regression will make more reliable predictions if your input and output variables have a Gaussian distribution. You may get some benefit using transforms on your variables to make their distribution more Gaussian looking. Rescale inputs. Linear regression will often make more reliable predictions if you rescale input variables using standardization or normalization. With simple linear regression, we want to model our data as follows. Y is equal to B0 plus B1 times x. This is a line where y is the output variable we want to predict. X is the input variable we know, and B0 and B1 are coefficients that we need to estimate that move the line around. The goal is to find the best estimate for the coefficients to minimize the errors in predicting y from x. Simple regression is great because rather than having to search for values by trial and error or calculate them analytically, use more advanced linear algebra, we can estimate them directly from our data. We can start off by estimating the value for B1, and this consists of calculating the means for x and y variables using training data. Means is the average value for the variable in our data set. We need to calculate residuals of each x from the x mean value. We need to calculate residuals of each y from the y mean value. Next, estimating the intercept B0 is much simpler since the values are already calculated. Given the representation is a linear equation, making predictions is as simple as solving the equation for a specific set of inputs. Finally, to evaluate the predictions made, using the assumed model representation, we can calculate an error score for our predictions called the root mean squared error, also referred to as RMSE. P is a predicted value and Y is the actual value. I is the index for specific instances because we must calculate the error across all predicted values.